All right, let's take a look at some calculations. And as I like to do, I like to keep calculation examples pretty simple. For the most part in this class, you'll calculate a couple of minor things, but we're not going to rely much on hand calculation. I only use it honestly as a tool to help you understand what's going on with these procedures. I don't have any. I mean, I don't think anybody needs to know how to calculate these things because it's a practical tool. It's more to help with your learning of it. So it doesn't look like it's magical when you get these numbers. See, I've got a small 3-group example. I have 4 people in each group, and you can see their scores represented. We can see an overall mean of 4.42. And we can see the individual mean values. There's also standard deviations here for each of the groups. So x bar sub t, the grand mean, that's going to be 4.42. Then the x bar sub j values, it's going to be 4.5, 1.5, and that's 7.25. Sums of square total amount of variability in the scores. This is not interpretable on its own. So don't try to look at these sums of square values and get any sort of meaning out of them because they're meaningless. They're squared values. So, already, it doesn't make sense to think about terms in that way. They're not interpretable on their own. The stuff we can do with them is where the real magic happens. You can see what we do for sums of square total. We take each individual score. So you can see I started with the first value, 3. Subtract from it the grand mean, 4.42, and square it. I did this for every single score. So you can see all 12 of the scores listed there. And it comes out to a little under 75. Again, what does that 75 mean? It doesn't mean anything. I mean, the only thing that it means is that sums of square between and sums of square total and sums of square within are going to add to that. All right, sums of square between. This is what can be explained by a group membership. That is, knowing somebody's in one group over another can tell you something about where they tend to score. If you knew somebody was in group 1, for example, you'd know that they would tend to score around 4.5. If they were in group 2, they'd probably be pretty close to 1.5. Group 3, they'd be somewhere over around 7.25. You can see the calculation here. We can express this in 2 different ways. I could take each individual, I could do this 4 times for each of the individual scores, or I could do the shortcut here. 4, that's the number of scores, 4.5, the first group mean, minus 4.42, the second group mean, and so on for all of the scores. We do this and it's 66.17. Again, that's not interpretable, but if we think about that in terms of how much of the total it is, that's a pretty big chunk. Then finally, sums of square within. This represents what we cannot explain. And again, this would be equivalent to sums of square residual in regression. You can see here we take each individual score and subtract from it the mean for the group. And we do that for every single score. Why the mean for the group? Well, again, if you think about things in terms of regression analysis, the mean for the group would represent our predicted score. If you haven't taken regression, just think, if I didn't know anything about the people in the group, only with their mean, what would be the best guess I could make of an individual score? Where would I be right most often? And the answer there would be, if you guess the mean, that's the most accurate guess that you can get. All right, degrees of freedom and mean square. Oh, it looks like I didn't do the first one. Degrees of freedom between group. That's just 3 minus 1, so 2. You can see the mean square calculation, just sums of square over degrees of freedom. And then finally, degrees of freedom within is 12 minus 3 for 9. And then we have MS within over DF within for 8.75 over 9. All right, F and the null. The null hypothesis here, since we have 3 groups, it's going to be simply that all the group means are the same. So mu1 is equal to mu2 is equal to mu3. We take our different mean square values and we calculate an F value. It comes out to around 34. Practically, you can think of that as being a pretty big value. And then the PF command here gives us the probability of our result. What would be the probability of getting a result this extreme if the null hypothesis were true? We can see that it's a very small value, 0.00000. That's really small. Is that less than 0.05? Yeah, that's clearly less than 0.05, so we would reject the null hypothesis. Now, if you want to see how we used to do it way back when, I take the F table, and I've got the wrong value represented here. Let me scooch that over for you. So we take our different degrees of freedom, 2 and 9. We line those up, and we get the value of 4.26. We could compare our F value to that. Clearly, our F value falls well above that, which would be in this reject the null hypothesis range up here. We don't really use this approach anymore, but that's the way we used to do it back in the day. And you'd always have to carry around these tables with you or a textbook. All right, the effect size, eta squared, that's the Greek symbol eta. Like T, where we express the size of the relationship using an effect size, we have a similar measure for ANOVA. It's on a completely different scale. And we can see we have 88.3 in this case. And for some reason that was represented with the wrong value there, and now that's fixed. So group membership explains 88.3% of the variability in score differences. Sorry, this is the dangers of adapting something from another course on full display. Sorry.